Let's now take a look at an example. So in this example, we have some current in an infinite plane. So we're told plane y equals 1 has some current capital K equals to 50 milliamps per meter in the z direction. And so I've drawn this pictorially down here. So notice I've got my coordinate directions. Z is going up, y to the right, and x coming out of the page. And so I've drawn this y equals 1 plane here. So this is our y equals 1 plane. So we have this k in the positive z direction. And so we're interested in finding our magnetic field intensity at 2 points, 0, 0, 0, and 1, 5, negative 3, both indicated in the drawing as well. So as always, I would recommend you pause the video and try to set up the problem or work through the problem entirely before coming back to the video to see the solution. So as we saw with our equation, we know that we should only expect to see a difference in the magnetic field if we're on a different side of the sheet. Otherwise, everything should be the same. So let's go ahead and work through using that equation and verify that's true though. So let's start by looking at our origin. So 0, 0, 0, which we see is on the left side of the sheet. And so let's go ahead and say we can define our normal vector. So remember our equation had a unit normal vector. And so that was from our current sheet to the point of interest. So in this case, that unit normal vector is going to be defined in this direction. And so we see that that's going to be the same, basing this on our coordinate system over here, as being in the negative y direction. So let's come down here and let's say for our origin, so for 0, 0, 0, we have that our unit normal is going to be in the negative y direction. And so plugging into our equation then, we have that our magnetic field intensity is 1/2 K. And so our K is 50 in the Z direction, milliamps per meter. And so that's our given information up here. And that's going to be crossed with our unit normal vector, which in this case we just said is negative y. And so we can do our right hand rule. So we put our fingers in the direction of Z and we curl them in the direction of negative y, and we see that our thumb is pointing in the x direction, so it's coming out of the page the same as we have our x up here. So we then just have, of course, 1/2 of 50 is going to give us 25, so we have this is going to be 25 in the x direction, milliamps per meter. So that would be our answer for our point at the origin. And so we could kind of double check that, and we could see if we put so we're again using our right hand rule, slightly different form of the right hand rule, but we're putting our thumb in the direction of K, and we curl our fingers, and we see at this point at the origin, it's going to be coming out towards us. Now again, that's not entirely accurate because we're kind of treating that like one filament when we do that. We need to remember that there are an infinite number of these filaments, but we can see that it should be coming out towards us at that point. Let's now consider our point 1,5, negative 3 on the other side of our infinite plane. And so in this case, our unit normal is going to be different. So again, it's from our sheet to the point of interest. So in this case, it's going to be in this direction. And again, comparing to this, we can now see that that's in our positive y direction. So let's come down here and we can say for our other point, 1, 5, negative 3, our unit normal vector is now in the positive y direction. So we plug into our equation, we say that h is still the 1/2 K, so 1/2 50 in our z direction. And now our unit normal that we're taking the cross product with is going to be in the positive y direction. So again, right hand rule, we put our fingers of the right hand in the z direction, curl them towards y, and we see our thumb is pointing into the page. So that's going to be negative x. And so I'm just going to bring that negative out front. So we have negative 25 in the x direction. And so really that negative comes from that x direction, but I've just pulled it out front. And that's still milliamps per meter. And that's going to be the answer for our second part. And so what we see is that the magnitude is the same. The only difference is the direction, and that is determined by which side of the infinite plane we're on. So really that magnitude is always going to be 1/2 of, in this case, 50, so 25. However, we just need to consider what side we're on. So really our x and z locations are irrelevant. The only thing we're looking at is our y coordinate, and sorry, that's our z. We want to look at our y coordinate here and compare that to the position of our plane. And from that, we can determine whether it's going to be in the positive x direction or in the negative x direction. And so again, that's what we expected from our equation, but here we were just sort of confirming that. So one other sort of interesting thing to look at, again, we don't have enough time to look at all the examples that I wish we could, but there's an interesting example, page 7-6 on page 315. And so what this deals with is a toroid. And so basically, we can think of this as some, let's see how to describe it. Basically some ring. So we have some ring structure like this. So this is some 3D ring though. And around that we have some coils. So we have some toroidal structure. And so I'm drawing this really poorly. But basically the interesting thing about this example is it relates the result from this toroidal shape back to a solenoid example from page 307. So a solenoid would be sort of the same basic idea, except we don't have the curved structure of the core, we just have sort of a cylinder for our core. So again, interesting example to look at, but unfortunately we just don't have time to consider it here.